Welcome! This lecture is about buffers and peak shaving. We are going to look at how buffers can help to control and reduce the peak energy supply and the costs, and to ensure a stable working of the equipment. If a lot of heating is needed in the room or the air handling unit, the heat generator, let's say a boiler or a heat pump, will be on for a long period, maybe continuously working for a few hours. But what happens if the heating load is low because the outdoor temperature is not very cold? Then the heat generator will go on for maybe 3 minutes, giving enough heat to bring the room at 20 degrees, and will then stop. And 5 minutes later, when the room temperature has decreased to 19.5, it will start again and will heat again for 3 minutes and stop and start again. This is not great for the mechanical equipment like the pumps and the valves. Most gas boilers can cope with that, but with heat pumps and their compressors, that may give more problems and decrease the service life of the equipment. And that is a good reason to place buffers between the heat generator and the emitter. A buffer is just a water tank filled with hot water where heat from the generator is stored. Instead of water, phase change materials or thermochemical materials can be used as well, with the advantage of their high latent heat. In this 4-pipe configuration, all heat produced by the generator goes first to the tank. The tank is then tapped to the room emitter or the air handling unit. On the same way, the colder water returning from the emitter goes through the tank, and a pipe at the other side brings it back to the generator. A cold buffer would be designed similarly, but this time the tank is tapped at the bottom, where the water is the coldest. When the tank is cold, it can deliver cold to the rooms and the air handling unit, while the generator is off, avoiding this way too many short on-off cycles. It is very important that the tank is stratified, making sure that there is hot water above and that it does not mix too quickly with the cold water below. The tank must be well insulated to avoid heat losses that would decrease the overall efficiency of the system. Let's look at the different working modes. The generator can be on also when no heat or cold is needed, charging the tank. The generator can also be completely off, while heat and cold are provided to the rooms and the AHU. This is called tank discharge. And third, both can take place at the same time. The generator brings heat or cold to the tank, and the tank delivers simultaneously heat or cold to the emitters. Next to avoiding short cycles, a main advantage of a buffer is to provide peak load capacity in such a way that the generators can be sized smaller. A tank is much cheaper than a heat or cold generator, so that is financially advantageous. Let's use the load duration curves to look at how it works. Imagine we decide to design our generators to only 300 kW for heating and 500 kW for cooling. We are then missing the peak load. However, if we let the generator work longer at its maximum load, like that, we can store the missing quantity of heat and cold in a buffer and use it when needed. Previous slide may be a bit abstract, so you see it now for a part of the Hawley profile on which the load curve is based. If I size my heater to 300 kW, just like we did, you can see here where are the possibilities to charge the buffer. In this office building, that would be at night, when little heating is normally done, because there is nobody in the building. You could do exactly the same for cooling. Additionally, with the increasing flexibility of energy markets, it may be very useful to store heat when the fuel price is low or when renewable energy is provided. And when the prices are high or the energy is non-renewable, you can use the buffer tank. That is also a way to steer towards more sustainable fuels. When using solar thermal energy for hot tap water or space heating, we have to deal with the intermittency of solar radiation, and therefore a buffer tank is necessary. The tank is charged, heated, therefore, when the sun shines. In this type of buffer tanks, there is a closed loop of water going from the solar collector to the tank. The tank itself is fed either by cold tap water or by the return water of the space heating. There is always an additional electric element or a gas boiler for additional heating of the tank when needed. What happens in geothermal grids is beyond this course on buildings' HVAC systems. However, as geothermal systems are expected to be more frequently used, it is worth realizing that buffering geothermal heat is an important issue. Geothermal plants are mostly designed to work year-round at constant load and cannot be controlled very easily. Geothermal pumps cannot be switched off that easily. They could be clogged and would not work anymore. If we imagine that the heating profile of the whole neighborhood that must be served by the geothermal plant resembles the one of our building, it would not be wise to size the geothermal plant like this. An enormous surplus of heat would be produced, see the purple surface, that would have to be destroyed. It is much better to size it like that. In the summer, the produced geothermal heat could then be stored in an aquifer thermal storage, for instance, to be used in winter. Finally, a last word about the design of buffer tanks. A disadvantage of these 4 pipe systems that you see on the left and that we used all along this presentation is that all water has to flow through the tank, causing high flow rates in the tank and more mixing and less stratification. The 2-pipe system is therefore often preferred, where the hot water from the generator can be directly led to the room and air handling unit when needed. If there is no heat demand, then the hot water from the generator is stored in the tank. And as third option, the generator is not working, but the needed heat is taken from the tank. This needs, of course, an accurate control strategy of the charge and discharge of the tank. In this lecture, you have learned why buffers may be needed. First, they ensure that the mechanical equipment of heat and cold generators does not need to start and stop too frequently. They also allow for buffering heat or cold when the prices are low or when green energy is available, and they therefore avoid the use of too expensive or carbon-rich energy. Buffers are also essential when using renewables for heating and cooling, and finally, they can help with reducing the peak load supply. Thank you for your attention. Goodbye.